Welcome to Lecture 4.3, Mixing Problems with Two Tanks. Recall that we've seen a problem like this back in the Section 2 lectures, and we got a system of two differential equations. Now, in the problem that we've seen, one of the equations we can solve for, and then we plug the solution back into the second one and solve for that. However, the problem that we'll see in this lecture is going to be more complicated. We're going to have water draining from tank A to tank B and vice versa, so we won't be able to solve for either equation explicitly, so we'll need to use our tools for linear algebra. Okay, so here's an example. Suppose tank A has 30 gallons, so let me sketch it up here. So tank A has 30 gallons of water, and there's 55 ounces of dissolved salt. And tank B has 20 gallons of water, and there's 26 ounces of dissolved salt. Moreover, we have a bunch of conditions for water coming in and out. Let me do it this way. So the first one, water flows into tank A at a rate of 1.5 gallons per minute. I'll just abbreviate this as G and M. I think you know what I mean. And the concentration is 1 ounce per gallon. We have water flowing into tank B at a rate of 1 gallon per minute. Oops, I forgot my convention. Oh well. And 3 ounces per gallon. Water flows from tank A to tank B at a rate of 3 gallons per minute. And it flows the other direction. That's supposed to be an M. Flows the other direction at a rate of 1.5 gallons per minute. And then water drains from the tank at a rate of 2.5 gallons per minute. And let me also add in these initial conditions. There's 55 ounces of dissolved salt in here and 26 in here. So I'm going to write that. How do I want to write that? How about I'll just write that on the side as x1 of 0 equals 55 and x2 of 0 equals 26. Okay, so as before, we want to find equations x1 and x2 governing the amount of salt in tanks A and B. So as before, we will use our rate in minus rate out. So let's first do tank A or tank B. I think I called it tank A, or tank 1, I guess. So the rate in, we got to be careful here because there's water coming in this direction and that direction. So this direction, the rate in is 1.5 gallons per, here I'll write it out fully, per minute times x2 of t ounces per gallon. Let's make sure that that's actually a 2. And then, oh, I'm sorry, that's the one coming in this way. I didn't. And then we also have water coming in this way, so that is plus 1.5 gallons per minute, and then that's times 1 ounce per gallon is the concentration. So if you multiply this out, this is 0.075 x2 plus 1.5. That's the rate in to tank 1. Now the rate out, this one is simpler. We just have 3 gallons per minute going out, and then the concentration is x1 of t divided by 30 gallons. Oh, I should probably mention that. Notice that the volume both of these tanks is constant because we have 3 going in from here and here, and we have 3 going out, and we have 4 going in tank B, 3 from here, 1 from here, and we have 4 going out, 1.5 plus 2.5. So okay, so the rate out is 3 gallons per minute times x1 of t ounces per gallon, and that's just per 30 gallons. Yeah, x1, that's the amount of salt, x1 of t divided by 30 gallons is the volume, and this is 0.1 x1. Okay, so tank 2, or tank B I should say, tank B, the rate in so we have so this water flows out of tank A into tank B, so rate in is going to be the same thing as above, so 3 gallons per minute times x1 of t ounces over 30 gallons. That's the amount of water that flows in through this way, but we also have to include this, so that's plus 1 gallon per minute times 3 ounces per gallon. And so we have 0.1 x1 plus 3. And then rate out so the rate out of this is so we could do this separately, 1.5 this way and 2.5 this way, but it doesn't really matter. The fact, I mean, when it all said and done, we have 4 gallons per minute that is leaving tank B. It doesn't matter if it's leaving from one pipe or from 2 pipes. The rate out is 4 gallons per minute times x2 ounces per 20 gallons, and that is 0.2 x2. Okay, so we get a system now. Let's write down our system. Let's see the best place where I can squeeze this in. I think I can do it here. Yeah, so x1 prime is rate in minus rate out. So that is this minus that. Let me organize this. So I'm going to write this as negative 0.1 x1 plus 0.075 x2 plus 1.5. I wanted to write my x1 before my x2, so it's rate in minus the rate out. And then x2 prime is, so rate in, it's this minus this. So it's positive 0.1 x1 minus 0.2 x2 plus 3, because again it's this minus this. So we got a system. We also have initial conditions, which are, I'm not going to rewrite them, but they are up here. So we could write this in matrix notation, and let's do that on the next slide. Okay, so here's the system that we derived in the previous slide in matrix notation. We can write it as x prime equals ax plus b, and we have an initial condition x of 0 equals this vector x naught. Now this equation, the system we say is inhomogeneous because there's a non-zero b term. If b were 0, we would say it's homogeneous. And even though this is not a single first order equation or second order equation, because it's a system, the structure of the solution is going to be very analogous to what we've seen so far. Namely, the general solution can be written as the homogeneous solution, which is what we get if we set b equal to 0 plus any particular solution that we can come up with. Now it's hard to find a particular solution in general. It's very hard, and really the only ones that we're ever going to be able to come up with are steady state solutions, meaning those that are constant. So what we'll do in the remainder of this lecture is we will find a steady state solution, and then we'll talk about our approach for how to solve the homogeneous equation. And that's something that we will actually not do until the next lecture. Okay, so back to the problem at hand. How do we find a steady state solution? Well, remember, steady state solution is a constant solution. That means x prime is going to be 0. So the goal, let me actually write this down. The immediate goal is to find a steady state or constant solution. And to do that, we set x prime equal to 0. And then we solve. So let's do that. So let's suppose that x prime is, let's set that equal to 0. And that, of course, is equal to ax plus b. So we need to solve this system of equations, ax plus b equals 0 for x. So let's write this as ax equals negative b. We can certainly do that, right? And then that tells us that, well, if A is invertible, and usually our matrix is going to be invertible because these numbers are not particularly nice and pretty, so it's going to take a really big coincidence for this determinant to be 0. In other words, this product minus this product to be 0. And we can see right away that this product times this product, or negative 0.01 times negative 0.02 is not equal to this product. So let's say that x, in this case, x equals negative A inverse times B. And now it's a little bit harder. If A is not invertible, then we can't say A inverse is, if the determinant is 0, we cannot say A inverse exists, so we have to solve the system by hand. Okay, so in this case, and we solve it by hand, there may not even be a solution, of course. Okay, so let's compute the determinant. The determinant of this is one of those things that I did ahead of time. The determinant of A is actually 1/80th. Again, the determinant is this times this minus this times this. And so A inverse, remember how to get the inverse? You divide by the determinant, divide by 1/80th, and then we swap the position of these two things, and we switch the sign of these two. So in other words, we write negative 0.2 and that's a 2 and negative 0.1. And then we swap the sign, SIGN, of the other two entries, so we have negative 0.075. And then over here we have negative 0.1. And then if we divide through by negative 1/80th, that's the same as multiplying by 80. So so this whole thing is just 80. And then if you bring 80 into here, again, I did this ahead of time, you got to trust me on it, it's just basic arithmetic. This matrix is negative 16, negative 6, so it should be a 6, negative 8, and negative 8. So in other words, the steady state solution, let's call it instead of calling it xp of t, I'm going to call it xss. So this is not just a particular solution, it is a steady state solution. So this is equal to negative A inverse times B. And so the negative of this is A inverse, and the negative of this makes it positive. So that is, let's see, so that is going to be 16, 6, 8, and 8 times B. So B is this guy there, so that's times 3 halves and 3. If we multiply this out, this product is just 42 and 36. So this is a steady state solution. So the first step, again, always is find the steady state solution, and do that by setting x prime equal to 0. Okay, so here is our initial value problem with the steady state solution. Now I want to show you where we're going to go with this. So let's plot x2 versus x1. So x2 is going to be up here. Now picture what this is going to mean. So our initial value, our initial condition here is 55 and 26, and which that means we are starting out with 55, say that's 55 ounces of salt in tank A, and 26 ounces of salt, say that's here, 26 ounces of salt in tank 2. So that means this is on the Cartesian coordinate, this is the point that represents 55 in tank A and 26 in tank B. Now, our steady state solution is 42, 36. And so that's going to be, let me sketch about where that is. So that this might be 42, and 36 might be up here. And so here is that steady state solution. Think of this as like a sink, that no matter where you start, if you start here, eventually the concentration of the salt, not the concentration, the amount of salt in tank A and tank B is going to dive toward this sinkhole type thing. So it's going to go something like this. We're not really sure if it's going to dive this way or do something else or go back this way, but and actually it's not clear, absolutely clear why everything is going to approach the steady state, but at least it seems believable if you think about the physical situation. So it turns out that no matter where you start out, everything is going to sort of sink in toward this steady state solution. And again, we will, in a few lectures, see how to determine which way these curves bend. But now this is just sort of a cartoon of a picture. Okay, so it would be much nicer if this steady state solution were at 0, right? If we could just sort of move it down to here. So here's what we're going to do. Let's change variables. Let's define a new coordinate system. I'm going to let, let's get my pen. I'm going to let y1 of t equal x1 of t, well, not plus, I should say minus 42, and I'm going to let y2 of t equal x2 of t minus 36. So if x1 and x2 represents the amount of salt in tank A and tank B at any time t, y1 and y2 represents the amount relative to this equilibrium point. Okay? So we're subtracting off the steady state solution. Okay, so notice, so I'm going to write this as y1 equals x1 minus 42. I'm going to drop the of t's from now on, and y2 is x2 minus 36, and so we can take derivatives of these, and we get that y1 prime equals x1 prime, and y2 prime equals x2 prime, and that makes sense. The rate of change of salt relative to equilibrium shouldn't be any different than the rate of change of salt, just the amount. Okay, so let's plug this back into our system. I'll put a semicolon here so you can tell them apart. Let's plug this guy back into our system and see what we get. So let me write. So I'm going to circle this and say let's plug this back in. So I'm going to say plug back into our system. And if we do that, when I say do that, actually, how about if I write it like this? So we'll plug back into our system, which was x1 prime equals negative 0.1 x1. Let me just write it out. .5 and x1 of 0 equals 55, and then x2 prime, same thing here. It's positive point x1 minus 0.2 x2 plus 3, and x2 of 0 equals 26. So if we plug this back into here, I'm not going to, it's a little bit messy. I mean, literally, yeah, so I pointed up here. I should probably have pointed down here instead. Same thing, though. So for x1 prime is y1 prime, x2 prime is y2 prime, and for each x1, for each x1, I'm going to put in, so if solving for x1, you see x1 is y1 plus 42, and x2 is y2 plus 36. So for each y1, I put in, or sorry, for each x1, I plug in y1 plus 42. So let me actually, so this is just y1 plus 42. This is just y2 plus 36, and I do the same thing. Again, I'm not going to do all the messy algebra. It's not bad at all. But what you get is you get a homogeneous solution. Homogeneous system, sorry. We get a homogeneous system, and it looks like this. So to summarize what we did this lecture, we had a mixing problem with two tanks, and from that we derived an inhomogeneous initial value problem, something that looked like this. And to summarize this, we take the following steps. First, we find the steady state solution. So we set this equal to 0 and solve the resulting 2x2 system of algebraic equations, and in this case we got this vector. Next, we changed variables to convert the system, which is inhomogeneous, into a homogeneous system. So we subtracted off this, so we defined y1 and y2 to be x1 and x2, subtracted off this steady state solution, and we got this homogeneous system. Don't forget to also change the initial condition. And in the next lecture, we will learn how to find the solution to this homogeneous system. It's actually not that hard. It involves eigenvalues and eigenvectors quite strongly, and it depends on whether or not these eigenvalues and these eigenvalues are real, if they're complex, or if they're repeated. But we're certainly going to do it with some easier matrices than this one here that involves all these fractions. So we'll start simple, but what I want you to take away now is that the general solution to this initial value problem, which is it's always going to have this form, it's the solution to the homogeneous equation plus any old particular solution that we can find, just like when we had first and second order ODEs and no systems. So in our setting, our solution to the homogeneous equation we are calling y of t, and our particular solution, the only one that we have any hope of coming up with, is the steady state solution. That does not depend on t, so we drop the of t here. We write that as xss. So we know how to do this, and the remainder of the chapter we will learn how to find this, and we'll learn how to analyze it and graph the solutions as well.